Slides. Oh, great, here we go. So as he said, I'm the CTO of Indico. We do some stuff with machine learning. I basically am a guy that plays with embeddings all day, and that's my credential. So really what I'm going to want to, this is kind of a quick agenda of what I'm going to go through, right? Deep learning, machine learning have been in the news a lot lately. There's a lot in there, and I really want to start by kind of helping us unpack a lot of that. What is interesting, what is real here, and how do we actually make this accessible to people that don't have the kind of compute footprint that you might have at a Google or a Facebook? So we're going to talk about what is deep learning, why is it so effective, why is it so hard for individuals to use, what exactly is going on underneath the hood, and how can we fix some of those issues so that this can be a little bit more accessible. Just for those of you that might be unaware, these are a couple of clips of how this has been showing up in the news. I don't think it's a surprise to anyone that machine learning is still going on this, almost decade-long hype train that seems to have no sign of stopping in sight, right? Everything from AlphaGo beating the best humans in the world at a game that we thought was going to be intractable for computers for many years to come, to people claiming that new AI being released is so dangerous that they can't actually give it to the world at large because the consequences, might be a little extreme. And I will say a lot of that is hype. Not all of it is hype, and there is some interesting stuff in here. This might be a little loose. Yep. And something that you're going to notice throughout the talk is that a lot of people, when they say deep learning, they say neural nets. I'm never going to say that word because it's not accurate. Instead, you'll notice me say network models a lot, and I just want to clear up any confusion ahead of time. What you think of as a neural net, I will call a network model. Why do I not call it a neural net is just because it's totally inaccurate, right? The term neural net comes back from the 40s when we didn't understand how the brain works, and we still don't, to be fair, and we didn't really understand how to make good network models, right? So there are kind of these two ideas that we had lumped together that were current in neuroscience at the time, and we've realized since then that A, that's not how the brain works, and B, none of those approaches actually work in a deep learning context today anyway. So there's really no link at all between deep learning models and sort of the brain, so just to kind of clear that up a little bit. And we've known that since about the 80s, but because it's sort of a catchy word and people really like to think that it operates like the brain, it does stick around a little bit. Might just go over here. Right, and just to make clear, this is not some random thing that I'm saying. Yoshua Bengio, specifically in sort of a 2015 paper, brings it up. Neuroscientists have kind of been critical of deep learning for a long time because it does not, in fact, operate like the brain, but that actually is totally fine, and he happens to be working very hard on trying to reintegrate those two paths. So before I go any further, let's talk about what's the big deal, right? Why is everyone talking about deep learning? What changed? What is interesting about this? So what I've got up here is a set of competition entries for a very popular machine learning competition called ImageNet. The idea of ImageNet is pretty simple. Computer vision is a hard problem. There's lots of different types of things that we're trying to recognize. So let's just get a whole bunch of images together. We're going to tag them all and figure out how well we can figure out, what's a dog, what's a cat, what's a plane. And if you look at this, it starts out pretty standard, right? So we start really in this kind of 0.3 error rate bucket. Everything is pretty similar to that. The competition was actually around for a few years before 2011. You saw pretty similar marks. And then you see something really shocking happens, is this entry down here, right? And more than that, what you find is that actually after 2012, after this one entry, everything seems to follow that path. Right? So we've clearly got some massive step function that happened. And this was AlexNet is the name of this paper. Right? So this was kind of the shot heard around the world. What happened is that deep learning was around for a very long time. Again, the foundations were around almost since the 40s, 50s. We were building them in ways that look similar to modern networks, in the 60s and 70s. But no one really thought it was very interesting. Right? In fact, people thought it was so uninteresting that as of 2012, there were really 3 main researchers left. Everyone else in this community had basically given up on deep learning. And this paper was actually written by Alex Krzyzewski, and he called his paper AlexNet. When he presented this at the ImageNet conference, everyone just sort of around the world, had their mouths gaping open. This was the paper that convinced everyone that deep learning was interesting again. And actually, 2012 was the first time someone had submitted submitted a deep learning paper to ImageNet, and since 2012, no non-deep learning approach has ever even cracked the top 10. Right? So this was an absolute step function. And in fact, it's gotten to the point where the ImageNet problem, which we assumed in sort of 2009 when this data set was created, would take us sort of forward for however long as we needed to go, now deep learning models are so accurate that we've actually crossed over the threshold of human accuracy. And what that means is that this data set is actually no longer useful. Now, it doesn't mean these are the smartest people, right? They just make very different errors. Honestly, what it means is that ImageNet has 120 different categories of dogs, and computers are a lot better at tracking 120 different dog breeds than people are. But the fact that we've gotten so good at this problem that this data set that we thought for a long time was going to be unconquerable is now solved in a lot of ways is why deep learning is so interesting. But why do they work so well, right? What is it about deep learning that makes it so radically more effective at problems like that than things that came before? To answer that, we're going to have to go on a little adventure. We're going to have to go back in time and tell you exactly how things used to work before deep learning to understand why this is so transformative. So if we just take traditional machine learning, right, and if you know something about machine learning, just throw it all away. We're going to start from the very basics. The problem is that for any machine learning model, we fundamentally need to get a set of numbers, and we're starting with something that is not fundamentally a set of numbers. So in this particular case, and I'll say ahead of time, I'm going to switch back and forth between image and text pretty consistently throughout this talk. The same principles apply. Some things are just more intuitive to explain in terms of images. Some things are more intuitive in text. So I have text. I need to turn it into a list of numbers. That's not necessarily an easy thing to do. So how exactly do we do it? And it has to be a set of numbers that has a fixed length. Right? So it's not okay to just take, the ASCII encoding of every letter because that's variable. So I need to have sort of a fixed length list of numbers that I'm going to use for my machine learning task. So how do I do that? And let's just do the simplest thing we could think of. So we're just going to make a really long vector for every word there is. If it exists, then that'll be index 1. Right? If the second word exists, that'll be index 2, and we just make a really long list of, let's say, 10,000 entries, and that's going to be our vector. It might sound a little silly and sort of stupid. This is actually how we do it, right? So this is called a count vectorizer, right? And this is how we've approached NLP for decades. And honestly, 80% of the things that we have today are not too far from this. This is sort of my obligatory math slide. This is just sort of a slight alteration on top of it. In sort of plain English, what this says is that rather than just counting the number of times a term comes up, if I have something like a and the, some very common word, that's going to look like a really big signal where it's not very important. So we'll just divide this by how common the word is overall, and this gives you sort of the TF-IDF vector, which stands for term frequency, inverse document frequency. This is like 80% of NLP. This is how we do it. 10,000 dimensional vector, and we just toss it into some other algorithm. Now let's talk about why that doesn't work so well, right? And these are not sort of surprising. You can tell it's a pretty basic approach. So here we've got a piece of text, and we're going to look at this in sort of a diagnostic context. So let's think about this in terms of healthcare. So we've got this patient record. We want to figure out if maybe there's something going on with this person. So first, we've got this person's name, right? John Malkovich. Now, the first problem we're going to run into is that Malkovich is probably going to be outside of our vocabulary. Right? When we took all of our starting text in, we defined our 10,000, number long list of all the possible words. We didn't see Malkovich. It's pretty rare, not very surprising. So that's out of vocabulary, so we actually just sort of have to wipe it out. Can't pay attention to that. That's a little bit of a bummer. That's actually not the biggest bummer, though. So let's look at the things that are a little bit more interesting. Let's say rather than just wanting to pull out a name, we actually want to pay attention to some other basic features, right? Like the gender, the location, and the age of this person. Gender, that's kind of doable, right? We're picking up on individual words. Those pronouns are pretty indicative, so we can probably get at that. Location, maybe, right? Winchester's a location, but a lot of those are going to be pretty rare, so a lot of those will be out of vocabulary. And it's really hard to necessarily tell. Winchester could be a location or it could be a rifle, and distinguishing between those when the only thing you know is the word Winchester showed up, really tough. You actually can't really do that effectively. The age, well, if he just said he was 60, that's maybe okay, but his 60th birthday is in 2 weeks. Now remember, we're only picking up on individual words, so suddenly we've got this concept that we can't really express in a single word, and that's tricky, right? I don't know exactly how we'd pick up on something like that. People will do things, you might hear the term like a bigram. So the idea is in our big TF-IDF vector, instead of saying that each entry is one word, now let's include pairs of words. So we can do 60th birthday, birthday is, those will all be entries. But you see, it's still not really getting at his age. For me to figure out that this person is 59, even though it's plainly obvious to a human, really tough in a TF-IDF context. And then we've got the hard stuff. Plays tennis, soreness in the elbow, right? There was a trip to Casablanca. All things, again, this is not complex stuff, right? This is the stuff that it's immediately obvious to any human the second they look at text, but also things that are really hard to capture in a TF-IDF vector. So these are some of the really key problems that we've been grappling with for decades and decades and figuring out, how exactly can we contort and twist the data to pick things out like this. And I don't want to say that we haven't made any progress, right? This is kind of a quick sense for the three things that I really broke down, right? The linguistic context, things like synonyms, local context, what's the verb, soreness in the elbow, understanding that soreness applies to elbow, out of vocabulary issues, we talked about. And we've come up with a whole sort of kludgy set of really point hacks that we can sort of use to kind of solve these problems sometimes, and there's tons of problems with all of them. Fundamentally, what ends up happening nowadays practically is you'll start with a TF-IDF vector. And then you find all of these holes in your model, and you're like, oh, man, we really can't pick up on that feature, so let's hand code that one, right? So you select your features, you start with the TF-IDF vector, you train some model, you figure out all the issues, and then you add some more features, and you add some more features, and you add some more. And you get stuck in this loop for years and years, right? And that's why machine learning is something that's so expensive and so difficult to do, is because it's so exceedingly manual. And people are doing this, right? People are typing in, oh, okay, if I see soreness in elbow, then I want to code this in a certain way, right? And it's almost entirely manual. And a lot of people don't realize this. They think machine learning is actually automated. In a lot of ways, it's not. So to break it down into more simple terms, the philosophy of a traditional approach says, I've got some raw data, I've got some text, I've got some image, I've got some audio, and I need to turn it into features, right? And I'm going to do that with human labor, right? That's how I get from my words into my list of numbers. And the model only takes care of going from that list of numbers to whatever the final task I'm trying to solve is. Now, deep learning fundamentally changes this in a way that is subtle but very, very powerful, which is that it removes that feature engineering from the person's control. It says, okay, human, you are no longer in charge of creating these features, and now the model is going to look directly at the data and directly produce an output. And it turns out, as you might guess, it's really hard to make features. People are very, very bad at this problem, and now that deep learning has kind of jumped into the fore, this is the primary reason. It's because deep learning is so much better at coming up with what the right features are. It's drastically better than humans, and best of all, it all happens automatically. And that's why you get such great accuracy out of this, because it generates much better features for you. But, what's the catch? Why didn't we just switch everything over to deep learning, right? I mean, it's a better approach. I mean, it's way more accurate on every problem we can find. But there's no free lunch. So this is sort of a recent paper. BERT, this was by Google a little bit ago. Training of BERT was performed on 16 cloud TPUs. Who here has heard of a TPU? Okay, yeah, a couple of folks. Basically, because these models are so computationally intensive to train, CPUs are what we have in normal computers. GPUs are specialized graphics hardware that we used for games for a very long time, and Alex Krizhevsky was one of the first people that figured out some really cool hacks that we could do to the GPU to make them apply to deep learning. We got like a 30x performance increase, and we're still compute limited, so Google actually went and created their own chip. So it's not a CPU, it's not a GPU, it's nothing that you can buy. It's something that only Google makes and only Google owns, and you can access through their cloud platform. So even using this specialized hardware, right, it's taking 4 days, right, with a total of sort of 16 cloud TPUs. But this is really specialized hardware, right? This is something that's very, very expensive. How expensive? Well, I did the math, and it's about $12,000. So that's it. And keep in mind, this is one run of your code. This is one attempt to train on a data set that's not even that big, right? And just think about that for a second. Right? Who here, when they write code, gets it right the first time, has no bugs, they only have to run it once? Exactly, right? So think about having a bug in this code. This is not even that bad, right? There's plenty of modern models that take, 2, 3 times this much. So you say, okay, maybe I don't need Google's TPUs. Maybe I'm going to try to train it myself, and I'll put together, a really high-end hobbyist rig. I'm going to put, 4 1080s in there. I'm going to spend, let's say, $5,000 putting together a really high-end computer. Well, then it's going to take about 6 months to train this. You really don't want an error in that case. So this is really the fundamental reason, right? Is these deep learning models, they work incredibly well, but because you're asking them to learn these features in addition to learning the problem, they're massively computationally intense in a way that traditional machine learning techniques just aren't, right? I mean, it's worlds apart, not even getting into the data. So what does that leave us, right? So we've got these traditional approaches that they work. They're effective, sort of like a traditional microscope, and they're very, very well understood. And then we've got deep learning that's kind of this like really big, complicated scanning electron microscope that solves a lot of the problems that we have with traditional microscopes, but it's so unwieldy and so costly that we can't use it, right? I mean, who here, could operate an SEM by themselves? Yeah, exactly. Deep learning is basically the same way. So in order to figure out how we're going to solve this problem, we actually have to understand what's going on inside of these networks, right? Like, why do they take so long to train, right? What is so complex about them, and are there any shortcuts? Now, I know a lot of people out there, and this is a quote from someone that's got like 6,000 upvotes on Quora, right? Nobody knows how these network models work. We have no idea what happens to the data after it enters the black box. Who here thinks this is true? That, neural nets are black boxes, and we don't really understand what's going on? Oh, that's actually pretty good. A lot of people do tend to agree with this, so I'll just say, if you do have this in your head, you might want to ignore the next couple of slides. It might be a little bit upsetting, because we are going to explain how these work. So, what exactly is going on inside of a network model? These are a couple of screenshots from a really, really popular paper that came out in 2014 by Zeiler and Fergus, who are now the founders of Clarify out of NYU. And you'll see a couple of things, a few different ways we have to kind of dissect exactly what's going on inside of one of these network models, right? We've got kind of the individual layers, so you can step through the model, and we'll go through this in a little bit more detail. You can figure out, what in the image are we really paying attention to, right? What are sort of the most and least important features of the image? So if I'm going to break this down in a little bit more detail, you can think of it like this. Right? And I'll say ahead of time, this is a very, very simplified version of how a network model works, but it's good enough for our purposes. So sort of we got the input over here on the left, we've got the output over here on the right, and what we're doing as we go from left to right is basically we're taking very, very simple features, right? Here, imagine these as individual pixels. And then we're learning to combine them in various ways. And you see at the start, pretty low level, right? We're talking corners, simple gradients, not a lot of space, right? We're talking 7 by 7 pixels. But as we go through the network, the idea is that the model learns actually to combine those lower level features into higher level features, into higher and higher level features till we finally get to the output and it says, this is a dog. And you can kind of get a quick sense, right? So this is layer 1, very, very basic. This is layer 2. You start to see some more interesting things, circles, spirals, things along those lines. Layer 3, you start to get actually some really interesting sort of honeycomb-type patterns. And these are just sort of this is kind of an example of an individual node here, right? So there's a lot more happening, but this is kind of a sample. And then just to give you a quick sense, because the paper was on 5 layers, these are kind of what the higher and higher level features look like. Here you can see some sort of duck and goose legs, right? You start to see these really sophisticated eyes. But this is the generic idea. If you kind of break open a network model, what's happening is that it's learning to combine sort of lower level features into higher level features till it goes all the way from, say, pixels or words or letters to whatever it is we care about. Now, here's something that's really unintuitive, though. Because if I were to kind of show this to you, right, and say, okay, if we just back up a little bit. So, I have some task that I'm training this on. Say this is ImageNet, right? In this particular case, it is ImageNet. I would kind of think, hey, I'm only learning to differentiate dogs and cats in that last layer. So if I'm trying to do anything else, maybe the rest of this isn't actually that useful. As it turns out, that's actually not quite correct for what is initially unintuitive, but I'm going to try to make it intuitive in a sec, which is that these features, these sort of intermediate layers, these hidden layers, are very, very generic. They're highly generalizable and actually not problem-specific almost at all. Which is weird, right? Because we're training it to do something. Shouldn't it be just learning to do that thing? So let me give you a quick example. So I'm going to give you a few examples here. And these are about a cancer drug, right? I assume not a lot of people here are oncologists, so they might not understand what this means exactly, but I've kind of coded them by sentiment, right? The top one, that's super positive. Middle one is sort of more middling, and the bottom one's a little negative. So if I show you enough examples of this and say, hey, I want you as a person to figure out which of these tweets are, positive, which of them are negative. You could probably do it, right? And maybe just think in your head, how many examples do you think you'd need to see before you could maybe do this at a reasonable level? 100, 200, right? Not that many. But now I'm going to give you another example. I'm going to ask you to think about the same thing. So now here's some other examples. Here's some other examples that are also positive and negative tweets. But this time, they're in Chinese. It's a lot harder, right? Maybe it would only take 100 examples to do the first problem. I don't know Chinese. It might take 10,000, 100,000 examples easily for me to figure out if these are positive or negative, because I have to learn Chinese to do it. And this is actually the same intuition to bring into the network models. As it turns out, the thing that's really hard about sentiment analysis, there's a last piece of figuring out, hey, what exactly does positive and negative mean in this context? But there's that whole 99% of the problem that has to happen first that we don't usually think about as humans, which is just learning English in the first place. And so it turns out, if you look at the network model, basically everything in front of that last layer is very generic. It's shockingly generic, right? Not completely, right? You can't take something trained on, just cats versus dogs and apply it to any old problem. But this is why these layers turn out to be a lot more generic than we think they would be. So now let's talk about this in particular. Let's look at this slightly different. So we've got our layers, right? Now let's just talk about one layer quickly. Let's talk about the one right before the output, because these are going to be the highest level features, right? These are the things that have kind of the most information packed into them. If this is sort of like basic English pronouns, this is, full sentences and concepts, and is sort of very high level. And the thing that's also great is this actually gets us our set of numbers that we were originally looking for, right? If we look at this a little differently, this is just another way of taking text in here, right, and turning it into a list of numbers, which is really nice, because that's what we want. And I'm going to, and this is what's called an embedding, actually. So, to be clear, the TF-IDF vector, that's also an embedding. This layer is an embedding, this layer is an embedding, that layer is an embedding. They're all embeddings, right? An embedding is just very, very generically any case where we're going from, let's say text in this case, and we do something to it, and we turn it into a list of numbers. But what turns out to be very, very interesting is that this is a slightly different way of viewing things, because exactly what does that list of numbers represent? The TF-IDF vector, that's pretty obvious. In this case, it's a little bit less obvious, right? Exactly what each of those numbers represent. They sort of correspond to those filters, right? This looks kind of like a dog, this looks kind of like a cat, but we want to think about them a little differently. So I'm going to do a quick kind of refresher on vector math, because it turns out a really powerful way to think about these. So here we've got, our basic 2D space. We've got 2 points, 1, 3, and 2, 1. We're going to call them A and B. Hopefully this kind of makes sense to everyone, as you've got 2 points. But you can also look at those as 2 kind of arrows, right? 2 vectors going from the origin to that particular point, and then you can think of them as something that has sort of a magnitude and a direction, right? So still with me, relatively straightforward. And importantly, from kind of a programming perspective, this is just a list of numbers, right? This is just 2 numbers in a list. It's no more complex than that. And then you can do some really interesting things like vector math. So if I add A and B together, I just stick them onto the end of each other, and then I get this new vector, A plus B, also 2 dimensions, 3, 4, also just a list of numbers. So I can do, you can do subtraction, multiplication. There's a lot of interesting sort of kinds of math that you can do with these. And then importantly, if I want to extend this to higher dimensions, that's just kind of 2 dimensions. Here I've got a 3-dimensional example, right? And here again, it's just a list of 3 numbers, pretty straightforward, but you can think of it the same way as a vector. But the vectors that we're working with, these network models are really, really big, so they're very high dimensional. So we have to learn how to think about things in really high dimensional space. And how do you do that? Well, let's say we wanted to visualize something in 14 dimensions. So visualize 3D, and then just say 14 in your head, really, really loud. That's the only way to do it, is a short. But it's actually fine, right? And so this is from Geoffrey Hinton, which is another one of sort of the big Goliaths in this space. So to think about the higher level spaces, just visualize 3D and say the number loud in your head. It's a pretty good way to do it. Okay, so now let's look back at this framing, and then we're going to take a slightly deeper look. So what we have is this way of going from text now, and we use some embedding method. This is our network model. One recent example is something called Elmo. And then we're cramming it into some really high-dimensional space. right? So just imagine, for instance, this is some 300-dimensional space, and that's pretty typical. The thing that's a little bit different than a normal space, if you think about this earlier slide, here you can think sort of each of these dimensions is flat, right? 4 is exactly twice 2, and it's all very flat and normal. Basically, when you go over to higher dimensions, things get a little bit more complicated. So the space sort of folds in on itself a little bit. There's a slightly complex structure. It's not super important to track those details. Just think that we've got now all these points in a really, really high-dimensional space. Another way to think of it is, why do we call it embeddings? Is you think about it, you're embedding words, sort of the blueberries, in the manifold of the muffin. Right? So, every one of these, you can think about it that way, right? You're just cramming words into the muffin. You're figuring out, hey, where should this blueberry go? Where should that blueberry go? And, you're kind of doing it that way, which is a kind of nice analogy. And importantly, what this really gives us, because again, we had to train that network in the beginning, is a way to add additional linguistic context. So here we're training this embedding method, sort of that original big network, with some other text. So Wikipedia is a really, really common choice here. And what that lets us do is basically add a whole bunch of linguistic context to any problem we're going to do downstream. We can train one really big network model once, and then we can use it for a whole bunch of downstream tasks, because now this embedding method works. So again, it's just a different way to view it, right? Really, this is the neural net, right? That is the network model, right? And this is what was one of the really cool initial examples in these embedding approaches. Like I said, you can do vector math. So what exactly do these higher dimensional vectors represent? And it turns out these are like points in concept space, is a good way to think about it. So this is one of the classic examples. It's actually from 2012, the original Word2Vec paper, which was one of the very, very first papers to kind of frame things as these embedding methods. So you can take your vector for king, you can subtract the vector for man, add the vector for woman, and the result is the vector for queen. Just think about that for a second, right? Because what we're really saying is that what we've created is this new, very large 300-dimensional space that represents concepts, right? And we can take a lot of these very simplistic mathematical operations, like addition and subtraction, and there's actually meaning in them, right? We've conceptually removed the concept of man from king, right? And then we've conceptually added the concept of woman back in. This is crazy, right? And again, I think it's important to know, it's not like we're intentionally designing it this way, right? This is kind of a happy accident. As it turns out, when you look at those intermediary layers, they have a lot of interesting structure like this. The space is very, very meaningful and does represent kind of the concepts encoded in these. So really, your goal with these embeddings is you want to get something that's as accurate as possible, right? And granted, you can't break everything down into simple terms like this. Any individual word has a lot of concepts in it. Not everything works perfectly, but this is a good example of kind of how to think about these vectors and the meaning in them. Now, as you might imagine, this isn't a free lunch, so the things that you really have to pay attention to when you're learning these, the first I touched on a bit, right? Sufficient diverse context. You look at the first network model you're training, yes, the features are very generic, they are very general, but they're not perfect, right? So you do have to make sure you are training that base model in a lot of context. Actually, it turns out Wikipedia doesn't work very well, because Wikipedia isn't really diverse enough. A fun fact is that the word I does not appear anywhere in Wikipedia because they don't allow first-person pronouns. Not strange for Wikipedia, but pretty bad for text. The cursive dimensionality just generically means that 2 dimensions is simple, 3 dimensions is simple. By the time you get up to 300 dimensions, things are actually really weird and unintuitive, and there's a lot of things implied by that, so that's the cursive dimensionality. And finally, effective benchmarking. It turns out, because we've added sort of this additional complication, this additional model as a part of training our big machine learning model, understanding exactly how well it's performing gets actually a lot more complicated. So you just want to be kind of conscious of that. But now let's take a little deeper dive into this, right? We've talked at a really high level. Look, we're training some network model to perform some task, and then we're going to use those learned features in something else. But there are a lot of different ways of doing that, right? There's a lot of different ways that we can train these models. There's a lot of different things that we've done over the ages, and it turns out some of these approaches work better, some of them work worse. So this was kind of the very first set of approaches, or word embeddings, right? And importantly, this is because we're only learning to embed individual words. We're not coming up with sort of the concept space for a full sentence or anything yet. Some really common examples, some of which you may have heard of, are word2vec, glove, fast text. These are mentioned pretty frequently. In practice, the way to think about this is you'll train your initial model, and then you've got a lookup table for each word, right? So you just look up, okay, this is the vector, this is the embedding for that particular word, right? And then I'm going to use it for something downstream. And the way that we train these, there's really two methods. One is CBOW, which stands for continuous bag of words, which really just says we're trying to predict this center word given the surrounding context, right? And the idea is that if we can predict the center word given the context, then our embedding is good, then we've got strong signal in there. If we can't, then it's bad. So it's kind of Mad Lib style. The other one is actually the reverse version of this, skipgram, which instead says let's grab the middle word and try to predict the external context on both sides. Again, the idea is, hey, if given the center word, we can predict what happened on either side, then we've got a good embedding, then we really understand what this word means. They work pretty well. It was a good start. This was really what dominated things from like 2012 to 2014. But it's got some limitations. Most critically, this only works on the word level. So if I've got a full sentence, we've actually really only solved one of our big problems. We understand synonyms, but we don't understand sort of context. We've still got out-of-vocabulary issues. So next, let's move on to text embeddings. And these are kind of more recent. This is kind of, think of that, 2014 through 2016, 2017. Again, some common examples of this, doc2vec, Elmo that I mentioned earlier. ULMFit was a really popular paper, I want to say 2018, by Sebastian Rutter and Jeremy Howard. But the idea here is that you actually train on sort of the full sentence. So here, if we've got kind of our full sentence here, and here we've got kind of the word vector for each individual word, we're going to learn to combine those somehow, we'll talk about how in just a second, to do something. And there's two different problem formulations here, right? So one option is we can say, okay, we're going to treat this as a language modeling task. So that says I'm going to read from left to right, and at each point, I'm going to try to predict the next word. So I'm going to try to predict that the next word is dog. Again, the logic is pretty similar. If I can predict the next word, I understood everything that happened before. The other possibility is I can have an explicit supervised task, kind of like the Twitter example I was using earlier, where I can know specifically that the answer to this is true, and if I can figure out that this is true, or say the sentiment of a tweet is positive or negative, again, the idea is I understand what's going on. This is an effective embedding model, and I'm learning things effectively. And there's a couple of different detailed ways that we go about this. One is a CNN style. CNN here does stand for convolutional neural network. That is what it stands for, even if it shouldn't. And the idea is that we look at fixed windows here, right? So here again, we've got the quick brown fox jumps over the lazy, that same piece of text. And the idea is these are called convolution filters, and the idea is these are going to look at kind of three examples, or three words, and combine that into sort of one piece of information. And then we kind of stride these so that we're looking at every group of three, so we've got more context here, right? It's better than the two words we could really get at with TF-IDF. It turns out if you try to extend bigrams to even sort of three words, it gets computationally just totally intractable. This is a bit more tractable, right? But we don't have a huge amount of context here. It's a little bit gross. The width of these really defines how much context we're going to have around these. So that's why there's kind of this second style, which is the RNN style, or recurrent neural network style of learning these embeddings. This is going to look a little complicated, but it's actually not that bad. So the idea is that you have this concept of kind of memory. And sort of in a similar way to a lot of the other problems we're looking at, you try to read left to right, similar to how a human does it. So you start off and say, OK, I don't know anything about this sentence. I have no idea what's going on. Next, I'm going to look at kind of the word embedding for this one. I have this this is called a gating function. And what a gating function does is it basically looks at my current understanding of this sentence and the next word, and it comes up with a new idea of what the sentence is. So it says, OK, based on this and the fact that this says this is now what I think of this sentence. And it does that again and again and again and says, OK, each time I'm going to update my understanding of the sentence a little bit more. It's a little hard to think about exactly how much context you're retaining. But if you think about it intuitively, right, if I go from left to right, because I'm keeping all the information kind of one vector here, things will tend to get washed out as you read from left to right. The things that happen more recently will tend to override things that you read a really long time ago. There's newer techniques called transformers that get around some of those issues if you want to kind of Google it on your own. But these two techniques take us sort of to the end of 2018, I would say. Yeah, and then the idea is after I read the whole sentence, I get to some prediction, and then either I'm predicting the next word or I'm predicting positive or negative, and I use that to make my embeddings a little bit better. Right. Sorry. So that solves really the second problem that we have, right? The first problem was synonyms, right, and that concept of linguistic context. This is really this problem of local context, right? How do we build up a larger amount of context across the words, right? How do we remember the when we're reading jumps? Because again, remember with the TF-IDF vector, we really only have 2 words. CNNs is a little bit better, but not by much. But we still have this problem of out-of-vocabulary issues, right? How are we going to solve those, right? We're still fundamentally relying on these individual word embeddings, and we still have that problem, so how are we going to resolve it? So this is actually where we come to the modern day. This is how sort of a lot of modern papers go, is that because we have this really powerful sense of context now, we actually don't have to do everything on the word level anymore. And this is pretty crazy. So this is this is the end of 2018, a paper called GPT. This was kind of the original snippet I had at the very start about creating an AI that's too dangerous to release to the world, which is not true, but it's sort of the same paper. And the idea is that rather than operating on full words here, they actually operate on what's called a byte pair encoding. It's pretty close to just sort of the programming idea of a byte pair and sort of the encoding of an individual letter. It's not quite the same, so it'll be somewhere between 1 and 3 letters depending on kind of the text that you've trained it on. But the idea is very much that you're dealing with sub-word level tokens here, right? So the idea is now, even if I see a word and it's out of vocabulary, that's actually not so much an issue, right? Because the same way that a person can react to a word they've never seen, which is you sort of break it down into small pieces, figure out exactly what makes sense, and then recombine it to learn something, now we can do that too. Now, think again. If we were to try to do this with sort of a TF-IDF approach, with a more traditional approach, oh my god, right? There's no way, right? Think about how much context do you have in 2 letters is none, right? You don't get any meaning from that. But the nice thing is that with these modern approaches, we have way broader context, right? We've got a lot more information that we're dealing with, and so we can actually reduce the thing we're paying attention to sort of a very, very small level, and we can actually still get things that work. But ultimately, the proof is in the pudding, right? So we've nominally solved these 3 issues now, right? So we've gone through the linguistic context with our word embeddings, local context with sort of the more sophisticated text embeddings, and finally the out-of-vocabulary issues with these modern approaches that have very, very long context windows and can operate effectively on individual letters, which is great. But do they work? And it turns out the answer is yeah, they work really, really well. So here you see kind of a snapshot through time. This problem is just sentiment analysis, very basic, super easy to benchmark, very understandable. So in this particular case, it's binary, so it's just positive, negative. So the important thing to note is this 0.5 line down here, that's random chance, right? That's totally random chance. Humans are about 90% accurate, so this is sort of the most accurate we could possibly be. Now look at this, TF-IDF, 0.5, we go up to 500 examples, we're 55, maybe 60% accuracy. That's really bad, right? I mean, that's a coin flip. It's very slightly better than random chance. These aren't even as data hungry as traditional deep learning models, right? But you'd probably have to get to 10,000 examples before this starts doing something reasonable. Glove, on the other hand, this is one of these word embeddings we were talking about, right? So this is kind of partway through, drastically better, right? Even as low as 50 data points, we're doing something really reasonable, right? We've immediately jumped up to sort of 65%, and you start seeing, though, it's a little noisy, it starts getting better very, very quickly, even at these very, very low data volumes. Again, like a typical machine learning problem, this graph starts at 10,000 points, so anything being learned at this low data volume is awesome. And then fine-tune, which is the GPT papers, or the more recent ones I'm talking about, even though these are working on individual letters or pairs of letters, it's actually more effective still. Granted, down at the extremity of low data, talking 50 examples, that's not quite enough context for it to build up yet, but very, very rapidly, even once you're up to 75, 100 examples, it's significantly better. And the most important thing to remember here, right? This technology, 4 years old. This technology, 1 year old. This technology, 60 years old. So in 60 years, we've made very, very little progress on text, right? The fundamental approaches that we used back in the 80s are still the approaches that we use today. We've just done them a little bit longer. these new embedding-based approaches, right, just in the course of the last couple of years, the same way that we saw that transformative shift in ImageNet, where 1 year we destroyed all previous benchmarks, right? The successive years, this became the only approach that we could take to the point where we started, matching human efficacy on a lot of these problems. The exact same thing is happening, on the tech side with deep learning with these other approaches. And now we've actually managed to extend that into the extremity of low data, which is pretty astonishing. So we get to have our cake and eat it too. So just kind of some final conclusions. Deep learning is great, right? It drastically outperforms basically everything that we did historically. But to be clear, this isn't something that you just should blindly apply to every task. Like I said, the real critical improvement that deep learning brings is that it does the feature engineering for us. So deep learning does really, really well when the right features are hard to understand, right? So all the fuzzy problems that people are actually very, very good at, right? Things like text, audio, image, right? Because encoding those features is really, really tough. Deep learning does super well. If you're talking about more traditional kind of structured data, think about, predict column 12 with columns 1 through 11. Maybe deep learning works better, maybe it doesn't, right? That's kind of more of a toss-up. But where the features are unclear, deep learning just absolutely creams the competition. But using deep learning, right? So one kind of fun fact is, as of I want to say 2015, there were roughly 300 deep learning experts in the world. A lot of the reason that number is so low, so shockingly low, is because, again, for decades and decades, nobody thought this was interesting. Very few people were researching it, right? And the tide has only just started to turn, and it takes 6 years to do a PhD, and it hasn't really been 6 years yet. It's better now, but not by much. And 80% of the people that know how to do these are at OpenAI or Google or Facebook or Microsoft, and not really anywhere else. But by breaking apart the networks, by understanding exactly what's happening inside these models at a deeper level, we can actually figure out how to reuse portions of old networks to solve new problems with radically less data, and in doing so, have our cake and eat it too. That's my talk.